Okay, well, thanks very much for coming out on a kind of a slightly soggy evening. We're going to take you to an even wetter place underneath the ocean in the South Pacific. And this is an ideal audience for us, I think. This is geophysicists. We're going to be talking about geophysics and geophysical flows. It's engineers. We're going to be talking about impacts on one of the largest infrastructure networks on our planet. So as you said, we're going to be talking about a whole range of different hazards that relate to submarine volcanoes. We're talking about some of the impacts for people and for infrastructure. And we really want to recognise a lot of different collaborators in this. This is a truly international effort, which involves a lot of collaborators, particularly from Tonga, from New Zealand, from industry, from academia. And it's been really a privilege to work with so many different people to try and understand these hazards. So some of this is going to be a little bit of a highlight of a paper we published towards the end of last year, following an eruption in 2022, and Izzy will provide some background to it, and also includes some of the work that's been done by PhD students, people like Jacob Nash at NOC, and some work by Lewis Bailey, who I see is dialed in online, so that's nice to see him there. So I'm going to shut up for a bit, and I'm going to let Izzy tell you about volcanoes. Okay,
thank you very much. Okay, we're talking not just about volcanoes, but about underwater volcanoes. I could flippantly say, oh, 90-something% of volcanoes lay under the oceans. I'm not going to do it. I've gone for 2/3, which is a more conservative estimate. But it's because not all volcanoes really are created equal in terms of the hazard they pose. So we've got a lot of them that lie at mid-ocean ridges, right, which are technically volcanoes, very important to me, spent 4 years of my life doing a PhD on them, but not particularly hazardous. But when we think about hazardous volcanoes, actually a lot of those are either submerged or partially submerged. So they're either completely under the water or a little bit of them is sticking out and the rest of them is underwater. So ocean volcano and water volcano as well, because lots of them are in lakes or have lakes, are quite important, those interactions. I'm just going to make this smaller so I can see my own notes. Oops, sorry. Oh, no, I'm not. Never mind. I'm just going to move it. Oh, they can't see it. Oh, it doesn't matter. Sorry. There's a thing I can see that nobody else can see. Anyway, so not all volcanoes are hazardous, but quite a lot of them are, and a lot of the hazardous ones lie in the oceans. And the ocean is a real blind spot, actually, for volcanic hazards for various reasons. Firstly, we haven't mapped all of the oceans in particularly high resolution yet. There are lots of projects that are aiming to do this. Seabed 2030 is the main one. Lots of people will probably be involved with that. But because of that, we don't really know where all the volcanoes are. This is a problem if you're trying to understand what hazards they might pose and to whom. But also, because we haven't mapped them or we haven't been there, we also haven't sampled a lot of them. So we don't know what kind of lavas they're erupting. We don't know what kind of eruptions they're having. And we don't really know how often they're erupting either. So actually, our knowledge of volcanoes that are under the ocean is much, much sort of more rubbish, I'd say, than our knowledge of volcanoes that are on the land, mostly because they're hard to get to and quite expensive to study. We also have almost no real-time monitoring of submarine volcanic systems. So we have some through seismic networks if they happen to lie near to one that's been put on land. But in terms of ocean observatories, there are really only 1.5 in operation. One of those is cabled, it's on a mid-ocean ridge, so not really looking at hazards. And the other one is on Colombo volcano, which is connected to Santorini in Greece. Other than that, not a lot of monitoring of submarine volcanoes at all. And that's, again, because it's really difficult and really expensive. But that means we also don't really know when these volcanoes are going through periods of activity, how active a lot of them are. There was a big surprise in the Tokyo Bay when they measured heat flow on top of a volcano called Omuradashi, which they thought wasn't doing anything, and it turned out it's really, really hot and in quite a dodgy place. And then finally, when you have magma-water interactions, you tend to create extra explosions. So we add a degree of complexity into understanding a volcanic eruption when we start flashing water to supercritical fluids and blowing stuff up. So they make eruptions a lot more unpredictable. So for all of these different reasons, understanding eruptions and understanding the hazards that they pose in the oceans is quite challenging. Now, in terms of hazards, what do I mean? We have all the standard volcanic hazards for marine volcanoes. So they make ash, they make pyroclastic density currents, they can have lava flows, all of these normal things. But there are also some specific hazards that we only really see or are only super serious if they occur in the oceans. The first one I'm going to talk about is flank collapse. Now, we get that on subaerial volcanoes, but when it happens in the ocean, and it's usually caused by things like seismicity or the volcano swells up and the slopes over-steepen and part of it will collapse. When it happens in the ocean, you displace a lot of water, so you can produce a tsunami, which I'm going to come to. So it can damage subsea infrastructure. Those flows will flow out a long way under the ocean. Once they become mixed with water and water supported, they can go a lot further than a sort of normal landslide. But also they can generate tsunamis. Now, volcanic tsunamis in the ocean are, well, all tsunamis kind of are in the ocean unless they're a lake, but volcanic tsunamis are particularly dangerous because normally a tsunami warning system will be triggered by a major earthquake. But with a volcanic triggered tsunami, we don't get that. So they tend not to trigger warnings. And they can be caused by a whole bunch of different volcanic processes. So if you have a pyroclastic density current that flows down the side of a volcano and enters an ocean, that can produce a wave. If the flank collapses, that can produce a wave. Lots of other different processes. If you have a caldera collapse, if you have a really major eruption, both the explosion itself and then the collapse of the seafloor can generate tsunamis. Now, they can travel thousands of kilometres. People will be very familiar with the hazard that they pose and the risk to life associated with tsunamis. So, yeah, really, really serious. There is a video that's going to play, but you'll get it in bigger and higher resolution a bit later. Then I already mentioned pyroclastic density currents. So these are big clouds of hot ash and gas that flow down the side of a volcano. Something particular happens sometimes, not every time, but sometimes when they reach the ocean. So if the conditions are right, you can partition that flow into a surface surge that travels across the top of the ocean, and then a submarine flow. And that surface surge, which is still superheated ash, fine material, sometimes even some dense material, it can flow a really long distance because it's forming sort of a steam at its base, which means the friction is really, really low. So we've seen them float tens of kilometres. I think the furthest noted is in the 80-something kilometres. And you don't want a pyroclastic density current or a pyroclastic style flow that's travelling that far because, again, huge risk to life, and also they can damage communities, businesses, infrastructure in coastal regions. And the last one is pumice rafts. These are a little pet project of mine. They don't tend to kill very many people. They are big floaty rafts of rock in the ocean. But they can be a real pain because we don't usually tend to notice them until they form. So they're formed by the kind of eruptions that we don't tend to monitor. We might see them in a satellite image. But for example, this raft, which is from an eruption also in Tonga, but a different volcano to the one we're going to talk about mostly today, we didn't know that this volcano had even erupted until some boats ran into this pumice raft. So they're quite sort of hard to predict, and they can be massive. They can be really, really big. And while they won't, run you down and burn you to death, they are really, really bad for ships, for vessels, and for coastal infrastructure. So if you get pumice into water intakes, you can shut down the propulsion for your vessel. If you're a small pleasure craft, they're pretty abrasive on your hull. And also they form these big rafts that wash into ports and harbours. So they can cut communities off from sort of infrastructure they rely on, like deliveries. And also they take out a lot of coastal defences, and particularly sort of like mangrove projects and those kind of things. So annoying, but not quite as deadly, usually. Now, I'm going to talk today, or we are going to talk today, mostly about a volcano called Hunga volcano. It was called Hunga Tonga Hunga Hapai at the time that this image was made, and we haven't remade it, so that's why it says that on here. It's a volcano just off Tonga, but as you can see, it's not sitting there by itself, so it's the one highlighted by the yellow arrow. But here we are looking northwards across the islands of Tonga, and you can see we're looking for about 70-ish, maybe 100 kilometres. There's tens of different volcanoes here, some of which have names and some of which don't. This is a really volcanically active area. All of these volcanoes have the potential to produce hazardous eruptions, although they've got a variety of different chemistries, eruption styles and frequencies. We're focusing on Hunga because it had a really, really quite exciting volcanic eruption in 2021, 2022. But that wasn't the first eruption that it had. It has also erupted in 2014 and 2015 and also in 2009. And then it's got some other eruptions before that. So we've got a relatively well-documented volcanic history for this volcano, but you can see that a lot of the volcanoes on here don't even have a name or an arrow, and that's because we really don't know anything about them. So the volcano eruption in Tonga in 2021, 2022, it started like most volcanic eruptions in Tonga do. We tend to have, we've got used to having relatively sort of friendly, pretty, relatively small volcanic explosivity index eruptions in Tonga. So maybe a VEI 1 or 2. Like, you don't want to get next to it, but it's probably not going to cause major catastrophic international damage. So the first phases of this eruption, and this went on for about 5 weeks, started very end of November, beginning of December 2021, mostly relatively small explosions. Some pumices formed, a lot of it sort of phreatomagmatic activity. Again, you don't want to get too close to it, but you can see it's not huge volcanic activity. It was occurring from the vent that you can see. This is a series of, on the left-hand side, there's a series of satellite images. The top one is from November 2021, so this is before the eruption started. And then the second one is from January the 3rd. And you can see the eruptions are focused on that same vent system. So it's the same vent that we'd seen erupt in 2014, 2015, and a pretty similar eruption style, relatively small, relatively friendly, little explosions, bit of phreatomagnetic activity. And it carried on that way until about January the 14th. Now, on January the 14th, we saw a bit of an uptick in how explosive it's getting. So previously, we'd had eruption columns that were reaching a few kilometres, maybe 5 or 6, into the atmosphere. On January the 14th, it ramped up a little bit. So they went out, Tonga Geological Services, who are pretty extreme, they went out and videoed it. I'm not sure I would have gone. And you can see it looks like a pretty big volcanic eruption at this point. So the plumes here are reaching about 15 to 20 kilometres into the atmosphere. So it's quite a lot more explosive. And if I just flip back to the previous image, previous slide, on those satellite images, you can see between the third and the fourth one at the bottom, all of that land that had been built out during the eruption disappears. So that had all disappeared during this sort of slightly more explosive period on January the 14th. Then there was another hiatus, and then on January the 15th, about 15 hours later, there was an absolutely enormous, unprecedentedly big explosion, and there had been really no evidence that this was going to happen. So this was the biggest explosion, or the most explosive volcanic eruption that we have seen this century, probably since Mount Pinatubo. And it also, the reason we have this lovely image, it's probably, or it is in fact, the biggest volcanic eruption that's occurred in the satellite era. So we have observations of this eruption that we didn't have from other eruptions that have occurred in the past. This is a really important volcanic eruption, partly because it was very, very explosive, and these are relatively rare, and therefore when you get one, you want to study it because you might not get another one for 30, 40 years. It had good satellite observations, but the other thing that was really useful about this region is that because it had been relatively active in the past, this area had already been mapped. So we had maps of the seafloor from before the eruption that we could compare to maps that were going to be collected afterwards. And they were collected by a whole bunch of different people, from Niwa to Shane Cronin's team, who did some mad stuff swimming over the caldera, and all sorts of other people contributed to producing these aftermaths. But having a map from before an eruption in the ocean is very, very rare. Most places, as I said, haven't really been mapped. So this was a really good opportunity to understand the seafloor impact of a major explosive volcanic eruption, which hasn't really been possible before. And then, of course, the other reason this is important is because it had really, really massive, devastating impacts locally, regionally, and even globally in other countries as well. This sort of simulation you're seeing is the pressure wave from the eruption. That travelled 3.5 times around the world. It produced some pretty big tsunamis, which I'm going to come to in a second. And it also made the national news for various reasons. So I mentioned it produced a tsunami. It actually produced several tsunamis, so they're still not entirely sure, actually. The wave buoys didn't record all of them. So it's based on eyewitness accounts. It's probably 4 or 5 major waves. The last one was the largest. This is video taken by a guy called Branko Sugar, who I've met, who is a real character, actually. And he was pretty cool taking this, even though you can hear him in a documentary talking about how he thought he and his children were going to die. But this is the picture of the wave coming from the first of these explosions. So he was out on a little fishing boat. They heard the explosion and they saw this wave coming towards them. And they were fine. They went into deeper water and the wave passed underneath them. But it's pretty incredible footage. And this is another bit of evidence that we've had for this eruption, which is really good eyewitness accounts and also video taken by mobile phones, which again is not really always been sort of possible in the past. So there's lots and lots of different evidence streams to study this eruption. This is another bit of mobile phone footage of a tsunami. Now, this is taken from the main capital city, and it's actually, this is the wave that's come through a lagoon. So it's quite small here. I've sat on this beach, so it's not that small. I wouldn't want to be hit by this. But here, where it's come across the lagoon, the run-ups are only maybe a few meters. But there's a peninsula out to the northwest on Tonga. I did look for a map ahead of this to put on this slide, and I couldn't find one, so there isn't one, sorry. But there's a peninsula out to the northwest in Tonga, and that had really, really big run-ups. It was basically directly in the path of this tsunami. And so the run-ups there were up to about 20 meters, and same on some of the other islands in the Hawaii group as well, which is to the north. So this was a really major tsunami event, even though some of the video, or most of the video, makes it look like it was only a few meters. And then the other reason that this was sort of globally important and became of global interest is that about 15 minutes after this eruption happened, and we saw this happen, we knew there had been a major explosion, a big volcanic eruption in Tonga. But about 15 minutes afterwards, everything went completely black. There were no communications with Tonga whatsoever. It got completely cut off from the global internet. And that's a bit suboptimal, actually, if you're in the midst of a major sort of natural disaster. You're trying to coordinate with various partners. You typically receive aid from other countries, and you can't get in contact with them. This internet outage happened about 5:40 UTC, but it's actually in the evening in Tonga. And it made the global news. People thought, oh, this is going to last several days. They're going to be cut off from the internet for several days, and actually ended up being a little bit longer. But it wasn't really clear what process had occurred to cut Tonga off from the internet associated with the volcanic eruption. We didn't know, and so this is why we sort of carried out this study, because I had been working on volcanoes in Tonga, Mike works with cables, and so we spotted a little opportunity for a grant application there. And the other reason it's really, I think, important to understand risks to hazards is this is some footage that's taken by a drone. This is, again, Tonga Geological Services video over that peninsula that I mentioned. So this is a resort. This was not a ruin before the tsunami. It was a working resort. Luckily, this happened in COVID, so these resorts were not populated. There was nobody on this peninsula that was killed. But you can see from one side to the other, you can see the ocean on the other side. Here, the wave hit the side of the peninsula and it went all the way over. So there's a village along a road in the middle here, and in other parts of this footage. And if you're interested, I've got it all, so we can have a look at it afterwards. But you can see people's houses that have been washed off their foundations across the road. If you walk around, you can see sort of shipping containers that have been toppled. So it gives you an idea of the force of the tsunami that had hit and the sort of devastation in the places where it had occurred. And again, luckily there had been evacuation orders here, so most people were not there when it happened. But if you want to coordinate to sort of relocate people, if you have a load of evacuated people like this, you really do need to be able to communicate between islands and between villages. And so if all of your telecommunications have gone down, it's almost impossible to do. And actually, most of the information about this eruption ended up coming to the Western world at least, ended up coming from some Australian and New Zealand flights that went over the islands a few days later. And they did eventually get some satellite connections set up once everybody found those satellite phones. So I'll pass over to Mike for a minute to talk about cables.
Yeah, thanks, Izzy. And we went out to visit the peninsula in Tonga Tapu a few months ago, and pretty humbling to see the devastation that happened there. But also pretty humbling to see some of the real world impacts of natural hazards that we study. And I guess these things, they affect people in faraway places. They also affect us. But not as much as they do in exposed and vulnerable places like the South Pacific. There's a network of, I'm sure you're all aware of, about 1.8 million kilometres of fibre optic cable that's about the diameter of a garden hose pipe that connects us all. It provides just over 99% of all digital data traffic, including financial traffic and the internet, social media, all these sorts of things. It's not satellites, it's less than 1% because of bandwidth and security issues. And so this network of about 400 cable systems keeps us all interconnected. And whilst there's about 150 to 200 instances of damage each year, most relating to accidental human causes, the global network's remarkably resilient. So in the UK, where we have tens of cable connections, if we break 5 or 10 of them, we probably wouldn't feel any impact on our daily lives. But we go to places like the South Pacific, where there are island nations like Palau and like Tonga, like Vanuatu, for example, that only have a single cable connection. So when one cable goes down, it really is a big deal. You can do less than 1% of what you could do in terms of data traffic, communications, telemedicine, e-commerce, tourism, financial trading. And so it's a huge issue. In the UK, for example, we have redundancy on the network. If cables break, we redivert traffic to other ones. We have ready access within 24 hours to cable repair ships. We have a large supply within the UK of replacement stocks. In places in the South Pacific, this isn't necessarily the case. So it really exposes these areas which are already exposed to a range of natural hazards like tropical storms, volcanic eruptions, and earthquakes.
Connectivity for Tonga is very important. You may be aware that Tonga, about almost 50% of its GDP is from remittances from families abroad. So when the connection went down, a lot of the people missed out on a lot of what they would normally receive as income. And that didn't start to come in. I mean, that was almost a week before there was enough connectivity so that people would start receiving their funds through the banks. And even the banks had difficulty collecting, so it was a big, business came practically to a standstill during that time. So it was quite scary for everybody.
So this is our colleague, Samisi Panuve, who's the CEO of the cable company in Tonga, really relating the fact that these impacts affected people. Businesses couldn't happen. 50% of the GDP is money that's sent from abroad. And not being able to make business transactions, not being able to actually get in touch with your friends and family is a real issue. And not being able to coordinate disaster response was an even bigger deal. So we're interested in the human angle. We're also interested in the processes. What did cause this cable damage? Why did it happen so shortly after the eruption, but not immediate with the eruption? And can we learn anything about submarine volcanic eruptions? Well, this is a bathymetric map of the seafloor around Hunga volcano, and as Izzy said, this was taken before the volcanic eruption. So incredibly, we have a high-resolution map of the seafloor before the eruption. And we discovered from Tonga Cable Limited that both the domestic cable, which goes up to the north and provides connections to a third of the population of Tonga, to the island groups up there, and the international cable, which goes out to the west to connect to Fiji, then on to Australia and the rest of the internet world. Both of these were broken about 30 kilometres from shore, and we know this from optical time domain reflectrometry. We can see how far the laser light gets and gets reflected back. We didn't know how far the extent of damage or burial to the cables was until the repair ship got out and went looking for the ends of the cables and simply couldn't find them, kept going and going. For the domestic cable, it had to go 105 kilometres to the north. That's 105 kilometres of cable which was damaged or buried by something. And for the international cable, 89 kilometres. So much that actually there wasn't enough spare in hand in Tonga, and 3 cable companies had to club together to donate cable to be spliced together to fix it. But that meant there was not enough left for the domestic cable. So whilst it took 5 weeks to repair the international cable and get them reconnected to Tonga Tapu, the island groups, which make up a third of the population of Tonga, weren't reconnected for about 18 months. So that's a long time. I'm sure some parents in the audience will be delighted about kids not being able to get onto social media, but it's a very long time to be without some of those fundamental services that you rely on from the internet. So we were able to get a vessel out, and this is particularly in collaboration with the Nippon Foundation and colleagues in Niue and in New Zealand, to get a couple of vessels out to go and map that area and get an autonomous surface vessel over the volcano and see what had changed. And for those of you interested in the resolution of the data and what can you discern from change detection, there's almost a kilometre vertical change in the middle, so it's actually quite easy to resolve that. We see a huge hole that's about 6 cubic kilometres in volume. And on the sides of the volcanoes, we don't see a huge amount of change, but the areas of blue here represent areas of erosion or material loss. So we see gullies and scours on the side of the volcano that are up to 120 metres deep. And as the gradient decreases on the flanks of the volcano and over the top of the poor domestic cable, we see up to 40 metres thickness of sediment accumulated. And these flows that we think sculpted and shaped these gullies and scours actually picked up an additional 3.5 cubic kilometres of material. So these are quite big numbers. So we think that it's actually these powerful flows of volcaniclastic sediment, which is shown by core samples that we took. We see these fining upward sequences of coarse volcanic material. These flowed down the side of the volcano and then were steered by the topography, which is made up of other volcanoes, and then eventually hit the international cable about 80 kilometres away from the volcano. So here's a video, this might not show, it's a bit hard to see with this light. This is made by Niue, of what we think is an underwater volcaniclastic density current, but a bit like a pyroclastic flow or a snow avalanche underneath the sea, moving at fast speed towards the poor domestic cable and then running out much further, and also obliterating pretty much all seafloor life. So these difference maps allow us to understand the nature of the flow. These crescentic scours allow us to see that these are almost like turbidity currents that are going through a series of hydraulic jumps, eroding and depositing on the seafloor. And as they made their way 80 kilometres away from the volcano, we actually found that the international cable had been swept towards the volcano by about 1 kilometre and not away from it. And this is because the flow had been steered around a seamount and then back towards the volcano. So a really tortuous and complicated flow pathway. We can see from sediment cores that these flows didn't just dump into the ocean and run downslope. They had enough momentum because they were so voluminous and so concentrated. They even went upslope 600 meters vertically. And we can place this in the eruption timeline that Izzy introduced, and we could see that this huge eruption happened, 57 kilometers, went up into the mesosphere, and then material came firing back down into the ocean. And as this column started to collapse, it dumped huge amounts of material into the ocean. And this triggered these density currents. And we see this initial massive eruption, and about 15 minutes afterwards, the domestic cable, which was only about 12 kilometers away from the volcano, broke. And then about an hour later, we see the international cable, which was about 80 kilometers away, broke. And this is really unique. We can see the triggering mechanism, the timing of those events, and that allows us for the first time to try and work out how fast these flows were going. No one's ever measured, because no one's been stupid enough to put instruments in the way of an underwater volcanoclastic density current. And so we think to get to the domestic cable based on these timings and distances, the flow was potentially going up to 122 kilometers an hour. That's just over 70 miles an hour. This is fast. And even 80 kilometers away, it maintains a speed of about 50 kilometers per hour. So still fast if we're placing this in the context of turbidity currents that shape canyons around the world. And what we've done is exactly that. We've placed this in the context, these speeds against other known events that are triggered by tropical cyclones and river floods in places like the Congo Canyon and offshore Taiwan. So evidence of cable breaks, including telegraph cable breaks, and instruments that have made measurements like acoustic Doppler current profilers. And we see that the flows here are long run out, but much faster than any flow that's ever been recorded. And so we were interested in why. And when we start to piece the puzzle together, as Izzy's introduced the eruption itself, material, huge volume, falling down from the column as it starts to collapse. It vertically enters the ocean onto slopes which are about 40 degrees steep. They start to rip up material. They bulk up by about a third, so they're now very concentrated on steep slopes. You're at a real sweet spot where these flows can just really run extremely fast. So we think it's these factors that explain why we get such fast speeds. And so we've talked about Tonga, and this was a surprise to us and a surprise to a number of people that these sorts of flows could be so damaging for subsea cables. But it's not a one-off. It is rare. And so we said maybe there's 150 to 200 instances of damage worldwide to the subsea cable network. But we've gone back to the first telegraph cables in the 1850s and 60s, and we can see there's evidence of damage to critical cables that cut off parts of Indonesia in 1883 as a result of the tsunami triggered by the Krakatoa eruption. There's many other examples as well. And so whilst it's rare, when these events happen, they can damage long lengths of cable, and they can disconnect some of the most vulnerable and remote communities on our planet. And one thing that we have discovered, well, this is you now, isn't it?
No.
No, it's not. It's not you.
It's you. I can do it then.
No. One thing that we have discovered is it's not just what happens during that eruption or the day after the eruption. We discovered that years afterwards, last year, we just got disconnected. Hopefully we're back.
Yeah, I can see.
Yeah. We discovered that there were 2 instances of damage to the domestic cable again, very close to the volcano, following a magnitude 6 and magnitude 7 earthquake. And so what we think has happened here is these earthquakes have shaken the material off the flanks of the slopes and caused a secondary hazard, a slope failure. So here we could be looking at years after these sorts of events, these sorts of hazards persist. And this is probably a common signature we're seeing in other places. The fabulously named Kikumjeni submarine volcano in the Caribbean off Grenada. We see evidence based on repeat seafloor surveys of slope failure on the flank of that volcano, which then led to a cable break. And we see from land-based broadband seismic networks, we see the identification of a T-phase signal, which is coincident with the timing of the damage to this cable. And initially, this was interpreted as this T-phase signal as a volcanic eruption, and now we attribute this to a submarine landslide event. And this is work that Lewis Bailey, who I think is online, has been contributing to. We also see impacts of eruptions up to decades after that initial eruption. So events like lahars, which are concentrated flows of volcanic sediment, which can occur after an eruption, or following big rainfall events that remobilizes previously accumulated material, can be flushed offshore. And in the case of St Vincent, recently we've seen damage of 5 important fishing sites by lahars, but also damage to more than 50 kilometres of cable, in some cases more than 10 kilometres offshore. So this impact of volcanic eruptions is not just constrained to the eruption period itself. This is now Izzy's point to pick up.
It is mine. Thank you. So yeah, so we've sort of identified a bonus marine volcanic hazard here, and 5 is harder to get on a slide than 4, so that's a bit of a pain. But this sort of dumping of material into the ocean as associated with volcanic eruptions produces a real threat for telecommunications, which are really, really important for remote communities. So is there anything really we can do about it? Well, it's pretty hard to avoid volcanoes if you're putting telecommunications cables in. One, because the run out of the flows that we've been talking about are over 100 kilometres. And if you think back to that 3D map at the beginning, those volcanoes are closer than 100 kilometres to each other. So each of them is going to lie within the danger zone of the others. There's no space there that isn't at risk. But also because a lot of the places we're connecting are volcanoes. So if you are connecting your cable to a volcanic island, you can't really avoid it. So if we can't avoid them, is there anything we can do to make them a bit more resilient? Well, better mapping is really, really useful. So mapping the offshore regions around volcanoes, mapping volcanoes that are near to population centres or near to infrastructure, incredibly useful. It gives us a lot of information about where hazards have occurred in the past and where they might occur in the future, as well as their scale and potentially their frequency if you get some good cores as well. That can be very useful. Also filling in the blue, or what we call the white ribbon, so the bit that connects the coastal sort of zone into the deeper ocean. It's very hard to map. There's been some work using satellites to try and fill it in, but understanding those connections between land and ocean are really, really valuable. Monitoring volcanoes, and we'll touch on this again, but if you were able to monitor volcanoes better, they tend to give you some warning that they're likely to erupt. Not always long enough in advance to do anything about it, but usually a decent amount of time ahead. And so even if you can't relocate your cable, you can probably bring in some contingency. Obviously increasing the number of routes, their diversity and their landing points, that really helps, but it's really challenging for small communities because making the business case for cable connections, even for a single population of 100,000 people, can be a challenge. Often nations have to work together and get support from people like the World Bank to even put in their first cable. So if you have relatively small populations, there is no business case for second cables. So there is nobody to pay for it, really. So it's ideal if you can do it, and it is happening more and more, and the cost of putting in cables hopefully will decrease. But if you're able to do it, that's kind of the best thing you can do. But if you can't do that, you can improve the ability to repair them if there is damage. So hosting larger local stocks of spare cables, so you don't have to wait for it to be manufactured for these kind of repairs. And something about natural hazards in the ocean is they tend to damage really long lengths of cable compared to if you just drag an anchor across them. And also the availability and sort of global availability of repair vessels as well for cable repairs. They require specialised vessels. Increased investment in backup low-level satellite communications, so things like Starlink, although there are quite a lot of complicated political things around this, both from governments and from the organisations that own those networks. That means that it's not always as easy in practice to use them as one might hope. And then finally, a better understanding of how hazards connect to each other, how long they last for after, say, a volcanic eruption, and what the connected hazards might be, and on what timescales those are likely to occur. So all of these things would, I think, help us to enhance the resilience of communities. Some of them are happening, some of them less so. So sort of starting to summarise, I'm just going to shift this out the way again. What we've shown is sort of a couple of different instances of cable damage, but specifically the Tonga one. It's given us some really valuable insight into something happening on the seafloor and the timing of that event. And actually, this happens for lots of cable faults. It tells us about processes occurring on the seafloor and when they're occurring, where we wouldn't otherwise know that anything had happened. So they're really, really useful. But the information we get just from an instance of cable damage is quite limited. We know that a break has occurred, or some damage has occurred, but we don't really know much more than that. But there is a real promising advance here using cables as sensors themselves. So there are opportunities to use the optical fibres that lie within the telecommunications cables as sensors on their own. So you can use them almost like rubbish, but seismometers. So they don't work quite as well as a normal seismometer. But you can sense things like vibration, changes in seafloor depth, and also waves. So that opens up quite a lot of opportunities for applying them to different deep ocean measurements. And the next slide, oh, I'm on here again, sorry. Oh yeah, I will not wrap up yet. I've got one more point to make on this, and that is that if we are able to get this technology to work, and if we are able to ground truth the signals that we're receiving well enough, we have a global network potentially of sensors that we can use without having to spend millions of pounds on vessels to deploy individual sensors and to recover them and then to look at the information. So we have a network that can measure not just volcanic activity, but also low-level seismicity in remote regions, deep ocean currents that are really, really difficult to measure and tell us about climate change. So there's real opportunities here, and the other real benefit of these is you're going to be getting that information in real time. You're not deploying equipment and recovering it later. So in terms of early warning systems, cables have real potential. So that's sort of where we're heading now with our research, and now I'll let Mike wrap up.
Yeah, so I think since the first telegraph cables were laid in the 1850s, we've been learning about geology, geophysics. We've discovered there was a ridge in the middle of the Atlantic as a result of trying to lay cables, and discovered it got shallow there. And we continue to learn things from cables, from damage, and as Izzy said, increasingly from the utility of fibre optic sensing in all of its forms as an opportunity for early warning system. So hopefully we've taken you from kind of a slightly soggy Kensington to a very wet part of the South Pacific, and then we'll deliver you for refreshments and some discussions in a few minutes. I guess our finishing thoughts. Submarine volcanoes, hopefully we've shown you that they can pose some known but also some surprising threats to coastal communities and the critical infrastructure like cables that keep us connected on a global basis. And they can be really, really extensive, much bigger than on land. We've learned a lot from cable damage and continue to do that. And this has revealed to us the fastest travelling flows on the seafloor, explaining why, and that they were triggered from eruption column collapse. And this is a process which is really, really poorly understood, but might be very, very important for a number of different reasons. And as Izzy started the presentation, hopefully we're a little bit better than we were a couple of years ago, but there's still a huge amount of work that needs to be done. Submarine volcanism, in terms of our understanding and the hazards that they pose, do remain a blind spot still, particularly in places like the South Pacific. And what we need are advances in monitoring technology to enhance hazard assessments, but also to allow us to understand those precursor signals that allow us and will allow us to affect early warning and mitigation measures in a meaningful way. So I think that's everything we wanted to say. We're going to stick around for questions now and afterwards. But yeah, thank you very much for the invite, and thanks for listening.